Okay, so this is chapter 2 of the Stallings text, and I think it's instructive to look at this and to also look at Rajane's textbook on the art of computer performance analysis. That's a great book, and it's the purple one that I mentioned in the previous set of slides. Definitely worth a read. So the subtitle of the text is entitled Designing for Performance, and that's kind of what we're focusing on here in this chapter. And there is a need for balancing the utilization of computer resources. The cost of computer systems have definitely dropped dramatically, while the performance and capacity of those systems continue to rise equally dramatically. In my notes, I say, well, today's laptops have the computing power of an IBM mainframe probably about 25 to 30 years ago, or even as recent as 10 to 15. And there's probably more computational power in your cell phone than was actually used to fake the moon landing. Anyway, computers have become so cheap that we actually pitch them away. And there's a recent article that I'll try to post entitled How Many VAXs Fit in the Palms of Your Hands. The VAX 11780 was the reference machine for the first spec benchmark that we'll talk about a little bit later. And the author answers this question based on the first spec benchmark. And if you hold one contemporary Xeon Gold 6354 in each one of your palms, you hold the processing power of over 400,000 VAX 11780s. So we've definitely improved quite a bit, 200,000 times. What that original VAX would do is what's available on those current chips. There's also a famous quote that I have here from Bill Gates, and I say quote, and I would probably put it into quotes because I don't think he really said it. That 640K ought to be enough for anyone. And a kid asked him about it in 1997 Wired magazine article. And the question was, I read in the newspaper that in 1981, you said 640K should be enough for anyone. Did you mean it when you said this? And the answer that Gates gave was, I've said some stupid things and some wrong things, but not that. No one involved in computers would ever say that a certain amount of memory is enough for all time. So another motivation is that businesses are relying on increasingly powerful servers to handle transaction database processing, support massive client server networks that have replaced the huge mainframe centers. And we talked about cloud computing a bit back in chapter 1. And despite all of this, the building blocks that we use are similar to the IAS that we also discussed in chapter 1. The little graphic here is from Gil Vidal's company VMRAX, and Gil's actually a great friend to the computer science department. He's hired quite a few of our students over the years. So definitely if Gil comes around, get in touch with him. He's a worthwhile guy to know. This graphic isn't in the text, but summarizes the section on microprocessor speed discussed in section 2.1 on page 47 of the 10th edition quite well. Among the techniques built into contemporary processors are pipelining, which moves data or instructions into a conceptual pipe with all stages of the pipe processing simultaneously. Branch prediction, which is a look ahead instruction code fetched from memory and predicts which branches or groups of instructions are likely to be processed next. Superscalar execution is the ability to issue more than one instruction every processor cycle. And in fact, multiple parallel pipelines get used. Data flow analysis analyzes which instructions are dependent upon one another's results to create an optimized schedule of the instructions. And then speculative execution is branch prediction and that data flow analysis working together that will speculatively execute instructions ahead of their actual appearance in the program execution, holding the results in temporary locations in hopes that you'll need them. And this keeps the execution engines as busy as possible. Another nice graphic that's included in the instructor slides, and I really have to tip my hat to Pearson for the design of their instructor slides, is this one. And while processor power has raced ahead at breakneck speed, other critical components of the computer haven't kept up. The result is the need to look for performance balance. That is, adjusting the organization and the architecture to compensate for the mismatch among the capabilities of various components. The problems created by such mismatches is particularly critical between the processor and main memory. So processor speed, again, has grown quite rapidly, but the speed with which data can be transferred between main memory and the processor has lagged badly. The interface between processor and main memory is the most crucial pathway in the entire computer because it's responsible for carrying a constant flow of program instructions and data between memory chips and the processor. If memory or the pathway fails to keep pace with the processor's incessant demands, the processor stalls in a wait state and you get valuable processing time that gets lost. One of the ways to attack this, and there are several different ones, are to do things like increase the number of bits that are retrieved at one time by making DRAM wider rather than deeper. Change the DRAM interface to make it more efficient by including a cache or other buffering schemes. We'll definitely see caches in this course. Reduce the frequency of memory access by incorporating increasingly complex and efficient cache structures between the processor and main memory. Includes the incorporation of one or more caches on the processor chip as well. And then increase the interconnect bandwidth between processors and memory by using higher speed buses and a hierarchy of buses to buffer and structure data flow. Input output also evolves too, and there's a graphic, figure 2.1 on page 49 that illustrates that, but I'm just going to go with PC low letter. And basically I/O is one of the slowest parts of the system, and oddly enough, printing is one of the toughest tasks that we ask computer systems to do. I'm old, so it's best for me to work for a paper copy, but we've eliminated a lot of needing to use as much paper, and I think I'm down to probably using like 1 ream of paper per year, which is something I would go through whenever we did a printed version of a test. So we're definitely evolving the input and output to be a little bit more quick. Improvements in chip organization and architecture have also taken place, and there are 3 ways to increase processor speed. One is to increase the hardware speed of the processor, and that's due to the shrinking in the logic gate size, more gates, pack them together more tightly, increase the clock rate. Propagation time for signals gets reduced because they're packed more closely together and shorter connections. And then increasing the size and speeds of the caches is the second technique. Dedicating part of the processor chip to the cache, and that allows us to decrease the cache access times. And finally, changing the processor organization and architecture. Increasing the effective speed of instruction execution and incorporating parallelism. So problems with clock speed and logic density. One, the power. Power density increases with the density of logic and clock speed, and if you have a computer that runs hot, that there's a problem with dissipating heat. The other is RC, or resistor capacity delay. The speed at which the electrons flow is limited by the resistance and the capacitance of the metal wires connecting them. The delay increases as the resistor capacitor product increases. As components on the chips decrease in size, the wire interconnects become thinner. That increases the resistance. Also, the wires are closer together, and that increases the capacitance. And finally, memory latency and throughput. Memory access speed, or latency, and transfer speed lag processor speeds. So here you can see how we've been attacking the problem in past and current trends. There are now typically 2 to 3 levels of cache between the processor and main memory. So we have increased the amount of caching we're doing. As chip density has increased, more of the cache memory has been incorporated onto the chip. And that enables us to have faster cache memory access. For example, the original Pentium chip only had 10% of its on-chip area devoted to caches. Chips now devote more than 50% of their area to memory cache, and we have more complex parallel execution strategies. We've received diminishing returns on the increase in clock frequency and power since the late 1990s, as you can see down there with the graph. The top line shows that as per Moore's law, the number of transistors on a single chip continues to grow exponentially. Meanwhile, the clock speed, that's the red, has leveled off to prevent a further rise in the power consumption. To continue to increase performance, designers have had to find ways of exploiting the growing number of transistors other than simply building a more complex processor. The response in recent years has been the development of multi-core computer chips. So let's talk about these multi-core computer chips, in particular multi-core mix and GPUs. So multi-core is the use of multiple processors on the same chip. provides the potential to increase performance without increasing the clock rate. And the strategy is to use two simpler processors on chip rather than one more complex processor. With two processors, larger caches are justified and you can share them. And as caches become larger, it may perform sense to create two and then three levels of cache that take place on the chip. MIC is mini integrated core, and this gives a leap in performance as well as challenges in developing software to exploit such a large number of cores. The multi-core MIC strategy involves a homogeneous collection of general purpose processors on a single chip, and usually more than 50 cores per chip. The multi-core MIC strategy involves a homogeneous collection of general purpose processors on a single chip. So general purpose GPUs, the core is designed to perform parallel operations on graphics data. And these are the ones that during the pandemic, you're probably having a hard time finding. Traditionally, these GPUs are found on plug-in graphics cards and used to render 2 and 3D graphics as well as process video, and used as vector processors for a variety of applications that require repeated computation. The next section looks at laws that provide insight, and the two laws that we'll discuss are Amdahl's law and Little's law, and they're actually unrelated, but they both give insights into the performance of parallel systems and multi-core systems. So let's look at Amdahl's law first. And a speed up in one technology or design does not mean an overall speed up in the entire system. And this was first proposed by Gene Amdahl in 1967 and deals with the potential speed up of a program using multiple processors compared to a single processor. And it can be generalized to evaluate and design technical improvements within a computer systems. And it illustrates the laws, some of the problems facing the industry in development of multi-core machines with an ever-growing number of cores. Software that runs on such machines needs to be adapted to take advantage of parallel execution. Some things just can't be done in parallel or can't be divided up. There are certain tasks that are, not, you can't subdivide. In software engineering, basically we call those atomic tasks. So, even if we had 100 programmers working on it, it's still going to take a similar amount of time. So some things can't be parallelized. So anyway, Amdahl's law considers the program running on a single processor, such that a fraction of the code, that's F, can be made parallel. The other fraction, 1 minus F, is sequential. That means you can't divide it up. It has to be done that way, and it takes the same amount of time. And T is total execution time of the program using a single processor. The speed up of the program using in processors is given by the formula 1 over 1 minus F plus F divided by N. And you can see that as it develops in terms of an equation. So when F is small, the use of parallel processors has very little effect. That is, when the fraction of the code that can be parallelized is very small, obviously it doesn't make sense to run it on multiple processors because it's primarily sequential. But as N approaches infinity, the speed up is bound by 1 divided by 1 over F. So they're diminishing returns for using more processors. Of course, if a large portion of it is can be done in parallel, then you're doing great. The other law is Little's law, and this is a fundamental and simple relation with broad application. So in a queuing system, if the server is idle, an item is served immediately. Otherwise, an arriving item joins a queue. That is, it has to wait. There can be a single queue for a single server or for multiple servers, or multiple queues with one being for each one of multiple servers. Under steady state conditions, the average number of items in the queuing system equals the average rate at which items arrive multiplied by the average time that an item spends in the system. So to summarize, under steady state conditions, the average number of items in the queuing system equals the average rate at which the items arrive multiplied by the average time that an item spends in the system. This relationship requires very few assumptions, which is why Little's law still finds a lot of use. We don't need to know what the service time distribution is, what the distribution of arrival times is, or the order of priority in which the items are served. Because of its simplicity and generality, it's extremely useful and it's experienced somewhat of a revival lately due to the interest in performance problems related to multi-core computers. So Little's law is one of the most commonly used theorems in queuing theory and allows us to relate the number of jobs in the system with the mean time spent in the system. So the mean number of jobs in the system is equal to the arrival rate times the mean response rate. And can be applied to any closed system or subsystem. So for example, the mean number in the queue is the arrival rate times the mean waiting time. And this little slide is taken from Raj Jain's Art of Computer Performance Analysis. So let's take a look at an example. Monitor on this server showed the average time to satisfy an IO request was 100 milliseconds. The IO rate was about 100 requests per second. What was the mean number of requests on the disk server? Well, using Little's law, the mean number in the disk server is the arrival rate times the response time. So you have 100 requests per second times 0.1 in terms of the response time, and that gives you 10 requests. Because that's 100 milliseconds, so 0.1 seconds. So basic measures of computer performance. Even if a processor has raw speed, it may not perform well in some programs based on factors such as compiler efficiency, the underlying instruction set architecture, and your choice of language in which you program things in. So one measure of computer performance is clock speed, and this is one that you hear quite frequently. And that's dictated by the pulse frequency of the clock. For example, 1 gigahertz processor receives 1 billion pulses per second. One increment of the clock is called a tick, and the time between pulses is called the cycle time. The clock rate needs to be appropriate for the layout of the processor. There are some problems with comparing clock speeds, and man, this is what we did back in the 80s and 90s. Is a lot of people would just look at the clock speed, and I'm probably guilty of that as well. Execution of an instruction involves a large number of discrete steps, such as fetch, decode, obviously loading and storing the data, and then performing arithmetic and logic operations. And most instructions on most processors require multiple clock cycles to complete. Some instructions may take only a few cycles, while others may require dozens. When pipeline is used, multiple instructions are being executed simultaneously. Thus, a straightforward comparison of clock speeds on different processors doesn't tell you the whole story about performance. A more complicated way is to look at the instruction execution rate. On a given processor, number of clock cycles varies for different types of instructions, and we can use a term called clock cycles per instruction, or CPI. And that's basically we can calculate this as the number of instructions cycles per instruction type I, number of executed instructions of type I, the instruction count for the program, frequency of the clock, and then the cycle time. And that can give us a different measure of performance. That is the instruction execution rate. Other ones are MIPS and flops. MIPS are millions of instructions per second. Another common performance measurement deals with floating point operations per second, or flops. And that's often given in millions of flops nowadays, but it used to be just plain old flops. And MFlops is equal to number of executed floating point operations divided by the execution time. And since we're doing it in millions times 10 to the 6th. So as an example, a program results in 2 million instructions on a 400 megahertz processor with the following instruction mix. We can calculate that CPI, or instruction execution rate, as 2.24 based on the instruction mix. There's 1 arithmetic and logic, 2 load store with cache hit, for branches, and 8 for memory reference with the cache. 60% of the program is devoted to arithmetic and logic, 18 with to load and store with cache hits. 12% is devoted to branches. Those are things like your go-tos, your jump less than, jump greater than type instructions in assembly. And 10% are devoted to memory references with cache misses. So you can actually calculate the CPI and the MIPS rate here. So different performance factors and attributes. The next in the cell indicates a attribute that affects a performance factor. Another thing that's talked about in this chapter is calculating the mean, and there are different ways of calculating the mean. So you're probably already familiar with the arithmetic mean, where you sum up all the different values and divide by the number. There are other ways of calculating the mean, and those are the geometric and harmonic. These are good because a single number can only provide a very simplified view of a system's capability. Single numbers do often get used for performance comparison, so it's worthwhile to know which mean they were using when they calculated it, because you can get very different results, and we'll see a couple pathological examples here. So the arithmetic mean, this is the one that you're familiar with. You sum the individual values and divide by the number of observations. And this is an appropriate measure that the sum of all measurements is meaningful and an interesting value. And this works very well for time-based values. It's directly proportional to the total time. If the total time doubles, the mean value doubles. And it turns out there are multiple algorithms that can be used in calculating mean value. And this has been the source of some controversy in the benchmarking field. So let's take a look at these alternative ways of calculating the mean. The first one is the geometric mean. That's the nth root of the observations multiplied together. And that gives equal weights to all values in the data set. For the geometric mean of a ratio, the geometric mean of the ratio equals the ratio of the geometric mean. And this provides consistent results when measuring the relative performance of machines, and it's less biased towards outliers. Another technique for calculating the mean is the harmonic mean. And these are useful when looking at execution rates. And it turns out that this one actually is the highest of the values. So the arithmetic mean is generally lower than the geometric mean and the less than the harmonic mean. So here's an example where we're comparing the performance of three different computers executing on two different programs. For simplicity, we assume the execution of each program results in execution of 10 to the 8th floating point instructions. Left half of the table shows the execution time for each computer running each program, total execution time, and the arithmetic mean for the execution times. Computer A executes in less total time than B, which executes in less total time than C. And this is reflected accurately in the arithmetic mean. Whereas the order should be A followed by B and followed by C. The harmonic mean actually gets this closer to right, because it actually, the arithmetic mean has A followed by C followed by B. The harmonic mean has A followed by B followed by C. So again, when you're looking at a benchmark, what version of the mean did you use? So a simple example can illustrate the way the geometric mean gives you consistency for normalized results. In the top table, which is 2.3a in the text, we use the same performance results we talked about in the last slide. In table 2.3a, this is the top one again, all results are normalized to computer A, and the means are calculated on the normalized values. Based on total execution time, obviously A is faster than B, which is faster than C. Both the arithmetic and geometric means of the normalized times reflect this. In the bottom table, the systems are now normalized to B. Again, the geometric mean gets this right, but now the arithmetic mean produces a different ordering. That's one that we definitely don't want. So benchmarking and spec. Again, millions of instructions per second, floating point operations per second are not always the best means of evaluating processors. Differences in instruction sets and instruction set architecture can give us different results than we might expect. And a benchmark is a standard or point of reference against which things may be compared or assessed. And a benchmark suite is a collection of programs defined a high-level language that together attempt to provide a representative test of the computer in a particular application or programming area. So what do you want in terms of desirable characteristics? You want it to be written in high-level language that makes it portable across different machines, representative of a particular type of programming, domain or paradigm, such as systems programming, numerical analysis, or commercial computing, something that can be measured easily and has a wide distribution. And there have been several standard benchmarks developed, many by SPEC, which stands for Standard Performance Evaluation Corporation, and that's an industry consortium. So the current one is SpecCPU 2017, and this is best known as the SPEC Benchmark Suite. It's an industry standard suite for processor-intensive application, and it's appropriate for measuring performance of applications to spend most of their time doing computation rather than input-output. Remember, we said the input-output was the slowest part. Consists of 20 integer benchmarks and 23 floating point benchmarks written in C, C++, and of course your old pal Fortran. For all the integer benchmarks, most of the floating point benchmarks are both rate and speed benchmark programs. And there's over 11 million lines of code, not code. So here is a sample of some of the programs: Perl interpreter, route planning, video compression, alpha beta search tree for chess, Monte Carlo tree search for Go, a recursive solution generator for our old pal Sudoku, and a general data compression algorithm that's written in C. And it's interesting that the recursive solution generator for Sudoku was written in old Fortran. So some terms used in spec documentation: benchmark, which is a program written in high-level language that can be compiled and executed on any computer that implements the compiler. System under test. The reference machine, this is a system used by spec to establish a baseline performance, and you compare against the reference machine, how fast your machine does it compared to the reference machine. Base metrics, these are required for all reported results and have strict guidelines. The peak metric enables users to attempt to optimize system performance by optimizing the compiler output. Speed metric is a measurement of the time it takes to execute a compiled benchmark, and it's used for comparing the ability of the computer to complete single tasks. And then the rate metric is a measurement of how many tasks a computer can accomplish in a certain amount of time. That's sometimes called the throughput capacity or rate measurement. It allows the system under test to execute simultaneous tasks to take advantage of multiple processors. So to run a benchmark, you need a reference machine. And for a long time, this was the 1997 Sun 2. For Spec 2017, it's the Sunfire D490 with 2100 megahertz Ultra Spark 4 chips. And it takes about 12 days to compile and do a conforming run. And calculate the runtime ratio of the reference run on the system, and then compute the geometric mean of the 12 runtime ratios, which yields the overall metric. And this is the spec evaluation flow chart graphic. So basically get the next program, you run it 3 times, you select the median value, and then you take the ratio compared to the reference with the system under test, and then you keep doing that until you've run out of all the programs, and then you compute the geometric mean of all the ratios. So that's it for chapter 2. Thank you so much for watching, and I'm going to stop the recording now.